And yep, live on YouTube and live on Twitch. Twitch is fast. Twitch knows instantly that I'm live, but YouTube is kind of slow. I guess Mrs. Susan has to fix some things. Okay, now, yesterday we wrote a program in assembly. What was it? The chap for chapter 4, this program, and this was not working. And what was the goal of this program? To take two 64-bit values from the user and then multiply them and print on the screen a 128-bit value. So this does not work. And I think that the reason is because we do not know how to pass in multiple inputs to scanf function, right? So what we are going to do is we're going to write this program in C and then see the assembly code for that program, right? Okay, 64-bit mul.c, right? In- Include standard IO in main, right? And yes, how do we define 64-bit number? How do I say that I want 64-bit integer type in C? Hmm, hmm, hmm. Chapter 4, 64-bit integer type in C. What were these commands? Shared. These are the logical operations. Um, yeah, 64-bit. Yep, this is it. This is for 28, and I just have to replace the 28. This is the whole goddamn program. 64 expected something. Okay. A comma B has the same type. Yep. And I also want a function. Should I? Okay. Instead of making a separate function to multiply these, I will just write the code to multiply them here in the main function. Okay. Now I want to get values for this for them. First, printf. Why did I do that? Enter values and nope, not a new line. And then this, and then scanf. How do I say that I want to get 128 with values? This thing, Excel. Okay, okay, XL, LX, yes, LX. It is not X, it is A, the name of the variable A that I defined. Unsigned long, but the argument has type. Okay, unsigned integer 64. So long, I have to use a long. Long is, yeah, 64-bit. So okay, shit. Okay, so LX stands for long, and I gave in the pointer to a long thing, and enter number in hex. Why is this program taking number in hex? Takes in two things, typecasts X into 128-bit integer and Y also into a 128-bit integer and returns the answer. Hmm. Okay, let's see how it turns out. Now enter not values but enter first number and then the same thing to get uh, to get the value for B, and then I have to multiply them, whose type is unsigned int. This was it, right? UINT, unsigned int. Yes, UINT 128. Why am I not getting a type thing for this? Product equal to. Why am I not getting an auto suggestion for this? That is okay. Unsigned int 128 t, type convert a into that and then multiply the type converted value of b to that. Okay, now we have the product. Now we want to print the product, but before that we have to get the first 64 bits and the second 64 bits, and the most significant 64 bits and the least significant 64 bits. How can we do that? We can do that by, I have 128 bits in this thing, in the product thing. How can I get the least significant and the most significant 64 bits out of it? For least significant, can I divide it and find the remainder? I can shift and store. Let's see, how do they do it? Yeah, yeah, that makes sense. Um, 164 and T low. So when I typecast into unsigned int of 64 bits, the value prod, then I get the least significant 64 bits. And now I can make, um, I can again typecast it, but before that, I can, how do I right shift 64 bit? Right shift, yep. If I right shift, then I get the U, oh, and prod U N and I. So when I typecast a 128-bit value into a 64-bit value, then I get the least significant bits of that value. Now, if I want to get the most significant 64 bits, then I can right shift the 128-bit value by 64. So the most significant 64 bits come to the least significant value place. And is this the right operation? No. For right shift, we do this. Yeah, that makes sense. Point arrows, the way that the arrows point, that is where the thing will be shifted to. Now, what is the percent thing that we have to write? Oh, what will come here in percent, which will tell the printf function that we want to print a 64-bit value here. What is the, what do you call it? Delimiter. Okay, 0, 16. Okay, 0 and 6. And the what does 016 mean? 016, 016, LX. Okay, that must mean it, something. So percent 016 LX. This is supposed to tell the printf function that we want to print a 64-bit value. But how does 16 mean 64-bit? Is it telling that we want to print 16 nibbles? One nibble is 4 bits, and if I multiply 16 by 4, I get 64 bits. Let's just do it and see what happens. Equals. Uh, Now I have to print both the low, the most, and least significant bits side by side. So for first is A, then we have B, then we have high, then we have low. Okay, and unsigned long, unsigned long. Hmm. Unsigned long. Unsigned long. Will this work? Okay, this does work. Wait, now let's first see if it works. Out, dot slash out. The first number. It will, let's just say 1, 2, 3, 4. The second number is also 1, 2, 3, 4. And that is what we get. And that is a, that is something. Okay, so it seems to be working. Instead of first, has to be, wait. I learned a shortcut to, I pressed F right now to find, and then I pressed F again because I want to find F. Now, if I want to go to the next character which I was looking for by pressing the F in the start, then I can press semicolon, semicolon. And now there is no next F in this line, so no matter how much semicolon I press, I do not go to the next character, next same character. But if I want to go back, I can press comma, I guess. Yes, comma, semicolon to the next, comma to the back. That is just crazy. Now, second. Okay, so this seems to be working. GCC 64-bit into out. Okay, what is going to be my number? 64-bit number. So I can write a hexadecimal value that is, oh, is it like the 16016 LX that we used there? Is it telling the printf function that this is the amount of 64, and this is the amount of hexadecimal characters which you want to print? That would make sense. Okay, so for a 64-bit value, I can press 16 things. F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ah, overflow. Okay, if I do one less, what then? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Enter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's do this. Ah, again, overflow. Memory overflow. Okay, let's do with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No overflow this time, it seems. Uh, it's functioning it. So now we know the function is working. Now I would like to see the assembly for this into 64-bit dot s, and what is the file? This file, and 64-bit dot s. Okay, that is just great that I have it there. Okay, that is a long file. What are the things that I'm declaring? I'm using star1, which is enter first number. Then I'm using %lx, which is a string, and then enter second number and enter the third. Four strings I have declared in here, and then this is the main function. And before the main function, it's all right. And now in here, first I subtract 1, 1, 2, which means, what does it mean? 64-bit, how many bits? 120. Wait, that is quite a lot. One number here defines 1 byte. So one 112 bytes, that would result in 800. What is 8 12s? Crazy. 80 plus 16, 96, 896 bits. Okay, 896 bits, 112 bytes. Okay, so I want to add 112 byte things to the stack pointer. Okay, then I do this. Wait, I want to see how do I call the functions. Okay, here I'm getting addresses. First, I get the address of star1, then the zeroth string, then the address. Then I call the printf function. Okay, okay. Here I call the printf function. Okay, and then I move the stack pointer, uh, the value of stack pointer in the ninth register, and then I subtract 8 from the 29th frame register, and then I save it to the 8th register, and then I store the value at the stack pointer, whatever I got after subtracting from the 29th register the value 8, and then I am in the 0th register getting the address for the one string, and the one string is .lx, the first argument that I want to give to the scanf function. Okay, and then I store, wait, I got the address of this here, and then I am storing at that place the value that is at the stack. Shit, this is crazy, whatever is happening here. Before calling the printf function, what the heck am I doing? Now, I know how to give arguments to the printf function here. left sudo 8 byte folded reload 16 byte folded reload 16 into 8 16 8 what the heck is 16 8 uh 15 8 shit, am I that dumb? Is it 128? Shit, wait, yeah, 128. Shit. uh so what is happening here? I'm doing some things at some places. I get this part. This part I get. We are calling the printf function, the printf label instruction, branching off to it by branching link, and then and the argument we have provided in the zeros address, that is the string, the address to the first character of the string that we want to print, and then we move the address at the stack pointer, which is supposed to be empty, an empty address into the ninth register. Then we subtract the value 8 from whatever is in the 29th register. Okay, and then we store the value that is in the 8th, which we got from this, and store it at the address, at the memory location whose address is at the stack pointer. So at the top of the stack, we store this address. Okay, we are storing an address at the top of the stack. And then we stored an address at the top of the stack. That makes, I guess, sense. If the scanf function wants its argument at the top of the stack, and the second argument which it wants is an address to store the location of the thing that it got, and 8 byte we subtracted 8 from here, right? So 8 subtracting 8 would mean 64 bits, and 64 bits is the value, is the amount of things that we want. Okay, okay, this is making some sense now. And then okay, in this part we got the address of the string, that is the first argument, and then we stored that address itself at the stack pointer 40. Okay, and this is what is this? No, this is nothing. This does not change the stack pointer, and this gives adds this to the stack pointer and stores from there. So did scanf take its argument? What is this function doing with the stack? Now at the top of the stack we have an address, and in the zeroth register we have a string. So is that how we do things? Okay, let's say that is how we do things. And then we get the address in the zeroth of the second string that is to be printed. And yes, and then we call the printf function. And after that, we load the value, whatever value is at the 40th address into the zeroth register, and the stack pointer in the ninth, and then we subtract 16 from the stack pointer because we subtracted 8 last time and we have not updated the stack pointer. After doing that, we um, store the value that we got after subtracting in the at the top of the stack pointer. But before that, we loaded the output value here, 8-byte folded spill, 8-byte folded spill. Okay, and then mm, we call the scanf function, and then we load unsigned into register. Uh, how can I get how to pass arguments to the scanf function? How can I know that? Okay. Hmm. Hmm. Let's start off by making some changes so that I know for sure what is happening. So in this part, we subtract 1 1. Okay, let's do till here. Understand this. Try to understand what is happening here. Yay, last time we were here. Last of us. Okay, this here and work. Okay, first of all, I have the stack and I have the stack pointer pointing at the top of the stack. And the top of the stack is like the stack grows downward. So the top of the stack is actually at the bottom. So we have the stack point before anything happens. We have the stack pointer here, right? So at the start we have a stack pointer. Let's say this. Let's call this address x0x10. This is the address 10. So stack pointer has the value 0x10 in it, and then after the first instruction, what happens after the first instruction? The stack pointer's value is 112 is subtracted from the stack pointer. Okay, so stack grows quite a bit. Now stack pointer does not point here. It is not pointing here anymore. Wait, I could actually get it back and take it below with me. Now the stack pointer points here, and this place and this address is let's work with the decimal instead of with hexadecimal so that we have a good understanding so we can do the maths easily. Now this address is 122 because the last one we supposed it was 10. So now the stack pointer points at 122. That is all the change that happened in the first instruction. Stack pointer has the value 122. 122. Yes, and the first instruction. That is it for the first instruction. Now for the second instruction, store pair. we store these two values, the value in the 0xp and the 30th, the frame pointer and and in, the frame pointer and the value at the link register. We do not care and know what is the value, the initial values. We are just storing them on the stack so that after our manipulation of the stack, we can get them back and exit the program with the same values in them that we started with. And we do not care what the values are. Now, we add we add 96 to the stack pointer and start storing these two in that. And these two take 8 bytes each, so 16 bytes. We need 16 bytes. And so yeah, when we add 96, okay, I messed up a little. Subtracting does not increase the value. So yes, and let's not take it 10. Let's take it, let's say, a good value. A good value would be something around, let's say, 256. 256. So initially we were here at 256, and then we subtracted 112 from 256. So we got 144 in the stack. So this is location 144. This is the address of this block. This is not the value that is contained in the block, right? This is the address of the block, not the value itself. And then the second instruction, we added 96 to this. So when I add 96 to this, what do I get? 144 plus 96 gives me 240, I guess. Yep, it gives me 240. So starting here, let's say this address is 240, and starting from this address, we store the contents of the 29th and the 30th register here. So this now stores the original content of the X29th register and X30 register, right? And but the stack pointer still points here. So we can say that um, 240, starting from 240, we have the contents of X29 register and X30 register. And now the third point, the third instruction. What happens here? In the add, we add 96 to the stack pointer and store it in the 29th register. Okay. In the third stack. In the third step, we update the value of X29 and it stores this value 240, which you get after adding 96 to the stack pointer, which is this. So this stores 240. Therefore, that X29 register stores the address for this thing, for this memory cell. And this memory cell stores the original address of the X29, original value. So X29 has the address of the cell which contains X29's original content. And now we don't know what the heck these, I don't know what this means. CFI dot CFI underscore offset. Let's see. Nah, dot CFI underscore offset. Boop, 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 boop. In M1 in R64 assembly for M1, what is the directive dot CFI underscore offset do? And what is it doing? It is taking some value and some, no, I have CFI def underscore CFA, CFI def underscore CFA and dot CFI offset. Let's see what they do. In AArch64 assembly, including the M1.cfi def and offset are directives used for call frame information. Call frame information, completely new term, which helps debuggers and exception handling mechanisms understand the stack frame layout. Okay, register and then offset defines the canonical frame address CFA. Canonical frame address. The CFA is the reference point for locating saved registers in the stack. It is usually set to stack pointer or frame pointer plus an offset. Defines the canonical. So this is for the debugger. This is not for us. This means the CFA. Okay, we are setting a value called CFA, which is equal to the 29th register plus 16. So I guess we are not manipulating the value of the registers themselves. So we can just eliminate these bits and I gotta erase this. Ah! Okay, that, only that. Now, getting on with the fourth instruction. What does this do? And well, this is basically the same thing. This, the fourth instruction gets into the X0 register the address for the string that is to be printed. And this is a beautiful D, by the way. Address of a string. String. Yep. Address of a string. String is beautiful. Now, after getting address, I just call the printf function in the fifth instruction. And the fifth instruction, I just call call print oh, printf. Yep. So we understand till now. We got these things are like this, and we have in the zeroth register the address of the string, and then we called the printf function, right? And now what happened afterwards? Let's see. Till scanf. The next scanf. First, let me erase this, all these things, and here. This is just too small. That's what she said. Wait, okay. Hmm. Uh, yep, this only. Increase the size. That is too big. But she didn't say that. Okay. Um, yep. Okay. Now, sixth instruction. What does this do? It moves the value of the stack pointer in the ninth register. So now the ninth register also points to this memory location. Sixth, the ninth register has the value that is in the stack pointer. Now, seventh instruction. What happens in the seventh instruction? In the seventh instruction, we subtract 8, 8 from this, that is, so that it points here, 8 bytes. Okay, we subtract 8 bytes so that now we have 8 bytes below this. So now x8 points to this, which whose first address is 232. Now x8 contains the address 232, and let's see what happens next in the eighth instruction. Eighth instruction, it stores the value, whatever this value, in the location of the ninth address, and the ninth address is this. Okay, so the 144 thing, 144 address cell has the value of the eighth register. So this thing has the value 232 stored in it. That is empty 8 bits, 8 bytes. Okay, and the ninth instruction then, that is a beautiful line by the way. Ninth instruction gets the address of this string that you want to pass to the scanf function into the zeroth register, has the address address for string, it has the address for a string. Okay, this has the address for a string, and then in the 10th instruction, what do we do in the 10th instruction? uh, we store the value that is in the zeroth register at a value that is 40 above the stack pointer. What is 40 above the stack pointer? 188. Okay, why do we do that? Mm, I don't know why we do that, but apparently we do. And let's divide this thing into 8 bytes, but that would take a lot of bytes. So let's say this is 1 byte, another byte. We need 5 bytes, right? So another byte, another byte, not a byte, groups of uh, 8 bytes, that is 64 bits. 1, 2, 3, 4, and This will this point to the fifth byte. If I add, yeah, yeah, I guess when I add eight to this address is the lowest of the 8 bytes in this cell. We are taking one cell as 8 bytes long, so this address 144 is the address of the lowest byte among them. And then if I add 8, I will get the lowest of this. And then if I add 8, the lowest of this, and then the lowest of this, and then the lowest of this. Now this one, the lowest is 184, right? And we are storing the address of string a d string, address of a string in 184th address memory location in the stack. So 184 address has the address of string. It has the address of a string. Yep. And then we call the scanf function. Okay. And at the time of calling the scanf function, the top of the stack has 8 bytes, 8 empty bytes, and the zeroth register has the address of the string. So, okay, the top of the stack has an address which is utilized by the scanf function, it seems. So in the 11th instruction, we just call the scanf function. Okay. Bring the X back. And okay, now we move ahead, move on with the next instructions. After the 10th, we have done till here. Now let's go to the next calling of the scanf function. Right, yeah, yep, use this. And increase the size. That's good enough. And then put it here, right here. Okay. And what does this do? It gets the address of the second string. Okay. This is the, what is it? It is the 12th instruction. 12th instruction gets the address. Wait, how long has it been? But we are just, okay, 50 minutes. It's been 50 minutes since we started learning this single one program that we can't get to work, make work. We are trying to figure out how this C program works in the assembly, at the assembly level. That is pretty cool. Okay, now the 12th instruction just gets into the X0 zeroth register the address of a string, address of a string that we want to pass on to this scanf function. And is this the same address as the first? No, it is different. Why is it different? What are these strings? First one is this. Oh, now we want to pass this is the address of the string we want to pass on to the printf function. Okay, that makes sense. Address of string, and then in the 13th instruction we call printf, or int, we call the printf function in the 13th step. Okay, 13th step we call the printf function, and now in the 14th step we get the value, load the value from this thing, this address back into the zeroth register, so we can pass it on to the scanf function so that we do not have to load it again. That is working genius. Okay, okay. LLVM. Okay, we are looking at you. Okay, you work hard. Okay. Um, what was his name? The man who created LLVM created the man behind it all. Um, call who created LLVM? Latiner. Yes, Chris Latner, born 1978. 1978. Uh, 1978. David Goggins was 3 years old back then when this man was born. Was born. Yeah, born against shell. Now, we call printf. We get, yes, yeah, address of the string in the zeroth register. We call printf, and then we load. Now, the zeroth register has the value, the address for the string we want to pass to the scanf function. Address of a scanf string. Address of the scanf string. Now, I guess then we no, we don't just call it. Then we move the value of the stack pointer in the ninth register. The ninth register was already pointing to the stack pointer. We didn't change it. Nope, it was pointing to the stack pointer, and but then we again do this. Okay, whatever. Ninth register now can again contains the value of the stack pointer. And then what do we do after it? Ninth register contains the value of the stack pointer, that is the 15th instruction. And now for the 16th instruction, we subtract 16 from 29th register and store it into the 8th register. Okay, we subtract 16. First, we subtracted this and we got this and we stored this. Now, the 8th register points to the this location, which is 224. Okay, that is where it points now. Okay, so okay, and then we will, okay, here the X8 register stores the value, the address 224. This is an address, not an actual value. Um, the value is an address itself. And then in the 17th instruction call, we store the value of the 8th register at the address which is in the ninth register, and the address in the ninth register is this. Shit. So now, um, we update the value which is this by 224, and that is crazy. So now the stack pointer has the value 224, and then after it We just call the scanf function 18. After it, we just call scanf. This is just crazy. I know it that this figuring everything out like this is taking time, but this is crazy. This is literally crazy. The way they manipulate a stack, this is crazy. Now, what I'm guessing is this memory location, these 8 bytes here, they store the result um, of the first input that this scanf got, and then these 8 bytes, these lower 8 bytes store the input that this scanf got, right? Yep. Okay. I think now we can improve our own program. Chapter 4. Okay. Here, what do we declare? Oh, instead of doing all this, we can just use the stack pointer. So we have to do that. But instead of everything else, we can use the stack pointer and okay, the string for the first input will be input 1 and it will contain ASCII keys, and the ASCII keys will be enter first number. That is what the ASCII will have. Input 1 and then we have input 2, enter second number. Okay, so okay. Now here, let me delete everything else that I have been doing till now. Okay, now what do I want? First of all, before everything else, let me store the value on the stack. Let me store the value of the frame pointer and shit. Uh, Wait a minute. I will be just back in a minute. Hey, es funktioniert jetzt. Uh, Maybe my voice is a bit too high. 15 decibels. I don't know if it is high or not. But yeah, my father was calling, and now here we are. So yes, we are going to write this function on our own. First, we preserve the original values at the frame pointer and the link register. And we also update the stack pointer. Now, we want to call the printf function. For that, first we have to get the string, the address for this thing, the address for input one in the zeroth register. And for that, we do ADRP address of page mm, into the zeroth register. And whose page address are you talking about? This, the input one. And then we store in the zeroth address the summation of the contents of the zeroth address and the page offset for input one, right? That is good. And then we just call the printf function. Well and good. Now we want to call the scanf function. For that, we need two things. We need we need a value. We need 8 bytes of storage so that our stack pointer, so that our scanf function, when scanf function can store the input, and we need the string. So we can get the string in the zeroth register. It is not input, it is fmt at page, add the offset to the zeroth register, fmt at page off. Now we have that, and now we have how the stack pointer has to be. Yes, we have to update the stack pointer so that it points to 8 empty bytes. Currently, wherever it is, we don't care, but we want to update it, add, and store in the stack pointer. Wait, the stack pointer does not has to contain 8 bytes of storage. It has to contain the address of that value. A, the stack pointer. We have to update the contents of the stack pointer. Okay, now let's just update and get a storage, get some space of about. We would need, let's just go bonkers and get 128. We have 128 bytes, and the stack pointer now points to an address that is 128 bytes. Now, I want 8 bytes, right? So I can, fuck, it has to be subtract because the stack grows downwards. So now the stack pointer points at a value. Let's go here, our own mental. That is my stack, very beautiful stack. Now here is the original as it was, and then I added 128 to the stack pointer. It's just embarrassing. Yep. Then I added 128 to the stack pointer. Now the stack pointer points to this byte. Now I want to get these bytes, these two locations. This is 128 bytes long. And this, let me tell you that this one chunk represents 8 bytes. Okay, 8 bytes, not 8 bits. It represents 8 bytes. Spelling is wrong, but it represents 8 bytes. So I want to get the address of the first byte among these 8 bytes, which I can get by adding 120 to the stack pointer and storing that value in the stack pointer itself. Okay, first of all, I have to get that value in a register. Let's say I use the eighth register for it. Right? So in the eighth register, I get the value by adding to the stack pointer 120. Okay, so in the eighth register, my eighth register points to this chunk, has the lowest address for this chunk. Now I want to store that address at the stack pointer. So store the value of the eighth register at the memory location whose address is at the stack pointer. This is crazy. And then call scanf. Now, what I'm supposing is that at this point, our scanf are these 8 bytes have the first input. Now, I have to call printf function again, which I can just do like this. Instead of input 1, I will be getting the address for input 2, and then I will call the printf function. Now I want to call the scanf function, and for that I need a couple of things. For that, I need the address of the string again back in here, just like we did here, right? Yes, and in the eighth, now I want the eighth register to point to this, so I can add to the stack pointer 112 to do that. So add and store in the eighth register and add to the this add is the correct thing here. 112 12, and then store the value, add the eighth in the eighth register into the memory location whose address is at the stack pointer, and then just call scanf function. This makes sense. Now at this point, both of these should have this these 8 bytes should have the first argument, and these should have the second argument. Okay. Hmm. That makes sense. And then I have the values. I want to multiply them. Hmm. I want to multiply and get the lowest 64 bits and the highest 64 bits. I will be storing the lowest 64, least significant 64 bits here, and the most significant 64 bits into these chunks of 8 bytes. And to get the address, I will store the address of this into the 8th register like we have been doing. Let's first store the address of the low, which we would get by adding to the stack pointer 104. So now add and store the value in the 8th register, add to the stack pointer 1088. Why is this like that? Hmm. Right, now I have this, and in the ninth register I will get the address of the lowest byte for this chunk, which I would get by adding 96. Yep, adding 96 to the stack pointer. So I have the memory address of the memory location which will store the lowest 64 bits in the 8th register and the highest 64 bits in the ninth register. Now I have to multiply, okay, which would be mul mm, unsigned multiply for 64 bit. I forgot the operation. Hi, hi, hi. What does this do? Extends them and gets the most significant bytes. So for okay, mul h high store in the 8th register. First of all, I have to get those values in some register. So not store, but load the first input value in the first register and its address. Shit. First, I have to get the address. Hmm. Address of the bytes, and I will get the address in the seventh, uh, in the sixth, and the seventh register. So, what do I have to get? Add to the stack pointer for getting this. I have to add 112, and for getting this, I have to add 120. So for the first one, I have to add 120 and the heck. And for the second one, which I want to store in the seventh register, I have to add to the stack pointer 112. Now I have the addresses for these two cells. Now I have to load the data LDR into the first register whose address is in the sixth register and load into the second register the value in the memory cell whose address is in the seventh register. Now, in the first and in the second register, I have the inputs which the user inputted. Inputs that the user inputted. Shit. Okay, now I want to unsign multiply high. That is, get the most significant bits in the, oh, not in the eighth register. Eighth, shit, I have to use some other registers. I will get the most significant bits in the third register, and then after getting the bits in the third register, I can store them at the memory location whose address is in the eighth register. Okay, so now in the third register, I will get the result by multiplying the contents of the first and the second register. Now I want to get the least significant bits in the fourth register, and for that I just use the normal multiplication. Now I have the most significant bits in the third register and the least significant bits in the fourth register. Now I have to store them in the stack into these two things. Low and high, why is this backwards? I should switch it. Um, um, nah, it was fine. Again, it is arbitrary. So, okay, now I want to store the value that is in the third register, which is the most significant bits. I want to store the most significant bits in, let's say, the address which is at the eighth memory location and store the least significant bits at the address at the memory location whose address is in the ninth register. So at this point in our program, these these two are also filled, and I think I have stored, what have I done? Yes, I have stored the most significant bits into this register and the least into this. So this one has the, I should write MSB, not this. MSB is in this register and LSB is in this register. Okay, here is, and now we have to pass all of this on to the printf function. Okay, and they have to appear in a certain order. The printf function takes its argument. No, they can be fine. They are fine. Okay, I have the address for this. I have the address for this. I have to use some register to store the address for this and for this. Okay, ah, crazy. Now, first of all, let's get the address for the string for fmt2. fmt2 string. Yep, that will be the first argument for our printf function. Uh, fmt2 its page and then add to it. It's fmt2 page offset. Okay, we have the first argument for the printf function, and now for the second argument, so I have to store those in the stack pointer. How the stack pointer points to the first argument. The stack pointer points to the second argument. So now do I have to provide the address for these in the stack pointer or these values themselves in the stack pointer for the printf function to work? So no, let's see in the C of C's, I guess. Okay, after calling here scanf for the second time, we do some things. We perform multiplication three times somehow, and then unsigned multiplication high one time, and add and do stuff. And do we call printf? Yep, we call printf here. We get the address of the first argument here, and we store quite a few things. The ninth register has the stack pointer value. Okay, it has 999999999. Okay, so seems like from this that we are storing the values themselves, not the addresses, but the values themselves. Okay, and therefore, in our representation, in our the format 2 string, first of all, we need the first argument. And where is the first argument? The first argument after this is in the first register, and the second argument is in the second register. So I have to load the value in the first register at the stack pointer, right? This is crazy. LDR load the value in the first register at the stack pointer itself. Then LDR, the value of the second register, which is the second argument for the third argument for the printf function at a location which is plus 8, the stack pointer. And then we have to store the MSB and the LSB. I hope this works. I hope this actually works. The MSB is in the third register, the MSB of the product, and we store it at 16 plus the stack pointer, and we shit. It is str, str, str store the contents of the fourth register at stack pointer with an offset of 24, and this should work. I hope it does. And then we just call the printf function. I have everything ready, and then I can just, yes, get back the original values. The stack pointer was updated. Hmm. Okay, so add and store to the stack pointer. What was the original value that we added? We subtracted 128. Now we will just add 128 to the stack pointer, and we are back, and we then load the values into the 29th and into the 30th register. And what are the values? The values are stored at the stack pointer, and then we give it an offset of 16. I just hope this works. 120 line. No, this is not 120 lines. This is all the code there is. There are also a lot of comments above. Now, chapter. Let's use LLVM chapter 4.s, and I want the output to be called out. Okay, enter the first number. I got this. What were the numbers we used before? We used this. I'll be using just that. 4. The second 1, 2, 3, 4. Is it the same? Is it the same? Is it the same? It is the same. It is the same. So we did it. We fucking did it. Okay, let's check for these two numbers. It did compile, right? It did compile into the out file. Okay. Out is the executable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And now two zeros and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I should see this, hopefully. And I did not see that. Oh, uh, shit. It did not work. Let me use the exact numbers. Maybe I messed up with them. This is the first, and this is the second argument. It did mess up. It did mess up. Where am I messing up? Where am I messing up? Is the multiplication not up to mark? Mm, 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 mm. Uh, chapter 4. Uh, what is wrong? Where is it messing up? Uh, what are the things is this using for multiplication? It is using simple multiplication and then unsigned multiplication for 64 bits. The high 64 bits. Okay. Why is it multiplying like 3 times? And then also shifting right somehow somewhere. Why are you doing that? Hmm. This is all the multiplication logic that they are using. Okay, and I am supposing that, okay, they have the numbers in the 10th and the 12th register, the first and the second input, okay, and the most significant bytes are multiplied by this, or wait. In the 10th and the 12th registers, is that it? Yes, the 10th and the 12th registers store the value and then they multiply 10th and 12th, store it into 9, and then multiply 12th and 8th and store it into 8th, and then 10th and 11th and store it into 11th, and then into the 10th register they store the multiplication high 64-bit multiplication of 10th and the 12th register, and then add the 8th and the 11th register. The fuck is happening? What the heck is q q0? The zeroth register, but q word is for one word, x is for 64 bits, w is for 32 bits. What is q? Q would mean quad, but quad is 64 bits, and for 64 bits you use x. uh, okay, okay, I am messing up somewhere. Let me once again see the compile the original C program itself. 64-bit, um 64-bit mul.c, and the output store it in out c out c nope out c. Okay, dot slash out c, and I want to give these in, ah, shit, messed up. Okay, this and this. Multiplication is different. Is my multiplication correct? Okay, let's see. Um, multiply two 64-bit hex numbers, hex calculator, add, multiply, subtract. Okay, multiply, and the second, ah, don't they have the full range? Yet. Oh yeah, that is what. Okay, for this, and the first two are also FF. Calculate. I want the answer in hexadecimal. Okay. Chat GPT, give me the multiply, or just this into this equal to question mark, answer in hex. Let's multiply to hexadecimal. Ah, oh, convert them back to hex. Okay, the answer given by the C program is correct. Where am I messing up? Okay, my MSV is correct. My LS, how many of, wait, my MSV is correct and its MSV is wrong. There is also an E in there. My MSV is correct. Their MSV is wrong. My MSV is at least correct. My LSV is wrong. How to find LSB. Wait, let me see the multiplication operations. To multiply two numbers and then get the least significant bits, uh, multiply operations with 64-bit results. That is what I want. Sign multiplication. So I give it two things and then I add or do something. Okay. Sign extend. No, do not extend them. I'm giving you the extended version. Mul add, mod, mul multiply unsigned. No, 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 no. Okay. Um, which AArch64 instruction can I use to get the LSB of replication of 264-bit uh, numbers? 264-bit numbers. Okay. One. Yes. 1 minute. Soldier's minute. Okay. Destiny. That is what I'm doing. My code. Chapter 4. That is exactly what I'm doing. Multiplying them. Yep. Right here. Multiplying them. And then get. What do I use? W. You just take the first 32 bits. Let's do that. Clang. Invalid operations. I have to provide in 32 bits. Okay. 64 bits. And chapter 4. I can just take this to the top. Hmm. Okay. Instead of W, I provide X. Oh, where is it? 22 here. Now, instead of W, I have to provide X, and here also X. Mm, Clang chapter 4 out into Shakaboom. That is 1, and that is the other. Okay, my MSB is absolutely correct. I'm messing up in the LSB. Full 64-bit value. Unsigned multiply high. Is it treating them as a signed number? That would be easy. In chapter 4S. Okay, mul here. If I do unsigned multiplication, let's see what happens with this. With Is there an operation for unsigned multiplication for normal unsigned multiplication? Mul multiply, mul add, mul subtract, mul negative. Using 232-bit register from Mul is the correct option. Operation. Wait, but maybe this is actually the correct answer. Let me ask Claude. How do I have to hide my screen? Uh, Anthropic. Anthropic? What is anthropic? Anthropic is in galaxy, right? Anthropic word origin. Anthropic. What is anthropic? Anthropic is just a company. Shit. Where did Anthropic come from? California. Ah, wait, but word. The Anthropic word. Anthropic is an artificial Anthropic PBC. PBC Studios, oh, which make physics videos. Okay, Anthropic is an American company founded in 2021. Wait, ChatGPT and Google. What is Anthropic? Ah, shit. Hell. San Francisco Bay Area. Claude Sonnet. Claude, Claude Sonnet. Claude Sonnet. Claude Shannon was the man who first used Boolean algebra in electronics. And from then on, computers have been using zeros and ones. He was the first man, and he did that in 1937, I suppose. In 19 Lord Shannon, 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 Lord Shannon, he's the man who did it. Uh, when did Lord Shannon use Boolean algebra in that 1937? That is okay. In 1937, he wrote the master's degree thesis, A Symbolic Analysis for X-ray Tube. Okay, we are getting distracted. Uh, what is the actual answer? This multiply by this equals question mark. Answer in X with 128 bits. Let's see. Let's see. Oh yeah, at least my MSB is correct. My LSB is getting messed up somehow. Then we use some other number. Out, or slash out C. Okay, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. That is 16 numbers, yes. A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. That is also 16 numbers, and this is what I get. Now for out, A, B, C, D, A, B, C, D, or maybe just copy paste. We get different answers and different MSBs and different LSBs. So multiplication process is not working properly, and for this, not even the MSBs are working properly. At least in the last one, I was getting a proper MSB. Wait, maybe I messed up in the input. Um, First number is this, and then second number is this. Okay, I was not messing up with the input. Um, yes, I want to reply. This multiplied by this equal to question mark and answer in hex with 128 bits. Let's see. Most probably this is correct. 29 at the end, and for none of us are correct. It seems like 77 in the starting. 73. What the heck is happening? Okay. Let me ask ChatGPT about who is correct. Let's compute. Okay. Okay, that is just totally different from any answers that we have got. Answer without any data loss. Answer, answer properly. Okay, let's compute the full 128-bit result. Okay, starts at 84. So why were you answering this thing? Oh, that is the same as this. 84 and ends at oh 09. Does not match any of the answers. Let's do some normal hex multiplication. Hex multiplication calculator. Yeah, okay. Let's just do this simple thing. Hex value is this. No, not plus, but multiply. Multiply them. Do I get? Uh, why is this hex value? Why are there? Okay, 5 into 2. I should get A there. A. Okay, so the thing is correct, working correctly. Um, A, B, C, D, and here also A, B, C, D. Or I can go full bonkers and do this. And let's see the input now. It has overflowed. A, B, C, D, A, B, C, D. That much. Let's. This is the answer for A, B, C, D, A, B, C, D, and dash out. A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Go fix it. Is it because I have to add zeros in the front? 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 6, 8. Let's see out C's result. What it does. 734. Oh, that is correct, and mine is wrong. I have to admit defeat? Okay, it has been 1 hour and 47 minutes, and I have been unable to figure out how to multiply two numbers. So what is happening? Okay? Let me add some more digits, some more numbers. So to get a can I wait? So I have to admit that there is something wrong, but I am calculating MSB and LSB differently. So, am I messing up with both? I think my MSB calculation is correct. And to check that, let me ABCD, ABCD, and let me ABCD, ABCD, right? Three times. ABCD, ABCD, ABCD. And I get some MSB here. And if I go with my program, my assembly program, And okay, at least the MSB is correct. 4, 5, 6, 7, 8. So 8 starting from here to 3, 4, 5, 6, 7, 8 till 1. Yes, MSB is absolutely correct. No mistake there. But now with this LSB is messing up. How to get do the LSB? LSB depends. mm, LSB depends on the first 32 bits, right? Yes, LSB depends on the first 32 bits. LSB depends on the first 32 bits. Shit. LSB depends on the first 32 bits. So I want to multiply the first 32 bits to get to the LSB. I'm totally messing up with the LSB. Let's see the LSB algorithm that they are using. They, as in like they, 64-bit dot S here. This is all that they are using, and I am supposing. Fucking hell. And fucking hell. Whenever, when are they using any load operations? After scanf, let's just go and figure out all of these, what they are doing with that, all of that, and shit, program is getting messier, getting big and big. Put it where it was originally and should select these also. Oh, because I'm moving a lot of things, that is why it is doing that. Okay, and then select all these along with these. Move. What the fuck? Yep. Oh, fine. Yep, that seems okay. Okay, now the next instructions. These are the next instructions that I do after scanf, that the program does after scanf. And what is happening in them? Instruction 19. What does the 19th instruction do? It takes, subtracts, okay, gives new, decreases 18.8 from the stack pointer and loads the value in here 136 into the um 10th register somehow, and this should not contain anything at this point. And No, not this. I'm fucking stupid. It is getting the contents of this register. It is getting the contents of this thing. This has the second now this value is stored in the 10th register, and this is the first input. Okay, and then arithmetic right shift the contents of 10 by 63 and save them. First 19, and in 19 we have 10th register contains the, let's say, first argument. We are using this for the first argument to represent first argument. And then in the 20th instruction, we are doing arithmetic right shift on the contents of 10 by 63 bits. Okay, that is okay. Now, the 8th register either contains all 64 zeros or ones, depending on the sign of this first entry, because the arithmetic right shift uh, only contain shifts the input by 63 bits and stores and the empty bytes, the most MS63 MSB will become same as the MSB before shifting. So either it is all ones or all zeros. Now for the 21st instruction, this program stores this this value into the 12th register. X 12, 12th register has this value. So X 12 has second input. Okay, and now 12, 22. What happens in 22? The same ASR in the 11th register. Okay, 22, the same thing that we did in the 8th register is now happening in the 11th register, has the sign of the second. Let's write one, that is the first, the sign of for the first, and now 11th also has all zeros or all ones for the second input. All right, now for 23, let me fix this. Take my mess somewhere else. Shit. No, nah, not that, not that. Oh, shit. Um, all of these, then all of these stuff. Just move that a bit higher and then go back. Okay, in the 23rd instruction, now comes the juicy part, the multiplication part. Now 8th, 9th has the multiplication for 10th and the 12th register contents. So 9th now, 23rd, 9th register now has the, I would say, LSB for our answer. Our answers LSB. 24th instruction. What will happen in the 24th instruction now? 24th instruction. 24th instruction multiplies 8th and 12th and stores it into the 8th register. What would that do? Uh, by multiplying, it is multiplying. It is not taking an and, it is actually multiplying. And if I multiply a number, any number, then it will overflow and or it would become zero. It will become zero in either case. Wait, I'm not multiplying it by one. I am multiplying it with the string of one that is similar to multiplying a number by 9999999. And any number if I multiply it by 99. So this eighth register either contains 1111, which in decimal would be equal to 9999, or not equal, but equivalent to 9999, or it contains 0, which would give 0. So if it is negative, if the contents of the 10th register, if the first argument is the 10th, if the first input is negative, if the first input is negative, then I have some mess here. Okay, right? Because then I would have ones and I would have some messy thing here, messy LSBs. So it either contains LS, it either contains mess, it either contains mess or zero, right? 25th, now the 25th register, 25th instruction does the same thing to the 11th register. Okay, now the 11th register either contains mess, like messy mess, and or zeros. And this depends on if the first argument is negative, then I have mess, mess for negative, and if it is plus, then I have zero. And if the second argument is positive, then I have zero. Otherwise, if it is negative, then I have a mess here. Now, 26th. For 26th instruction, this is what I'm exactly doing myself. Uh, Now the 10th register has the MSB. Ah, I only stored LSB in the ninth register. Yeah, in this instruction, like not me, but they, they shit, as in they who are watching the Big Brother. Now, I add the contents of 8th and 11th register. What are, it could be mess or something or something something. Shit. 27th register. In the 27th instruction, what do I do? I store either mess. 8th has the summation of x 8th register plus uh, the 11th register, and then I add the contents of the 10th register. My MSB is just fine. I don't know what the heck is happening here. Am I multiplying to get these? Let me see what he did in the book. And it has already been a full stream, and we have been unable to figure out one single thing. That is how we can multiply two 64-bit numbers to get a full 128-bit answer. Now, the AArch64 implementation executes the multiplication steps with the two instructions. Most of the code is reverted to calling printf and scanf and moving parameters into positions. How is this multiplying? Move, 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 something, something. Printf, printf, move, move. Where are the multiplication, 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 mul, mul, mul. That's just it, isn't it? So we are using this exact logic, but they are not using this exact logic. So for all intents and purposes, our code seems to be correct. And today that is all we did. We got this code, but what did we figure out? We figured out that we figured out all these things, and that how we can manipulate the stack pointer to get whatever we want, and to provide, we now know that to provide argument to the, yeah, well, that actually makes sense because printf function wants numbers, not pointers. The printf function, um, here it expects values, values, not addresses, values as its second or third or any other argument, which correspond to whatever is the percentage thing that whatever is the delimiter, percent delimiter we have provided in the argument of the first, in the first argument string, right? But scanf function wants address as its second argument. The first one is a string, but the second argument is an address. So therefore, we provide it some addresses in the stack pointer. We provided some addresses in the stack pointer. So we don't leave the stack pointer empty, or we don't add any value. We add, we put in the address of the memory location which we are giving it. The address has to be there in the stack pointer, which could point to another location in the stack pointer itself. That is crazy, and we can just when we are done with it, we can just go back. We can just like right here at the end, we can just make the stack pointer as it was before and go back. That's it. So this was good. We wrote, how long is this code? Oh, that is a 63 line assembly code. Not much, but that just doesn't even multiply properly to 64-bit numbers. But oh yeah, that was good. And now we go back, and bitrate dropped, and just bitrate was having a war during this whole time. Shit, I was not sitting in the middle.